In this lecture, we continue our discussion on nonlinear programming. We mentioned in the earlier lecture that the focus is primarily on quadratic programming, but in order to understand the principles, we need to look at the basics of nonlinear programming. In the previous lecture, we were looking at a constrained optimization problem with inequalities as constraints. So, the constrained optimization problem with inequalities would be of the form maximize z equal to f of x subject to g of x less than or equal to 0. Now, we have already mentioned in nonlinear optimization or in particularly in nonlinear optimization, we do not have an explicit condition that x has to be greater than or equal to 0. So, if there is a restriction that x has to be greater than or equal to 0, then it has to be included as a constraint in the problem. Therefore, all these constraints can be written in the form g of x less than or equal to 0. We take the case where we wish to maximize and we derive the conditions for it. Every minimization problem can be written suitably as a maximization problem with suitable changes in the objective function. Now, the guiding principle is first to convert this inequality into an equation, then use the method of Lagrangian multipliers and take it into the objective function. So, this inequality is written as an equation by using g of x plus s square equal to 0. The s square comes because we do not have an explicit restriction that the s should be greater than or equal to 0. If it were linear programming, we would have written this as g of x plus s equal to 0 and said s greater than or equal to 0. Now, here we will write it as g of x plus s square equal to 0, so that s can be positive or negative or 0, s can be less than or equal to, greater than or equal to or equation, but s square will be greater than or equal to 0, so that g of x plus s square is equal to 0. Now, remember that this g of x plus s square equal to 0 is a set of constraints. Similarly, z equal to f of x is a function that involves more than one variable. So, we would have x1 to xn as variables. In general, we say n variables and m constraints for this problem. Now, we take this to the objective function by introducing Lagrangian multipliers, as many multipliers as the number of constraints. This is also called dualizing the constraint and bringing it into the objective function. So, we now define a Lagrangian function L, which will be f of x, and because it is a maximization problem, we would put it as minus lambda into g of x plus s square. Now, partial differentiation of this with respect to x, lambda and s would give us the conditions for the optimum. So, there are three sets of variables: x, which are the given decision variables in the problem; s, which are slack variables. So, we will have as many slack variables as the number of constraints, because each constraint is written as g of x plus si square equal to 0, and then we take it into the objective function by introducing lambdas. So, we will have as many Lagrangian multipliers as the number of constraints. So, we have this L, which is the Lagrangian function. Now, dou L by dou x equal to 0 would give us del f of x, minus lambda del g of x equal to 0. Dou L by dou s, which is a slack variable, would give us 2 lambda I si equal to 0. The 2 comes here, we differentiate with respect to s. So, this becomes 2 times lambda s equal to 0. So, 2 lambda I si equal to 0. Differentiating with respect to lambda would give us g of x plus s square equal to 0. Now we modify these three conditions. We also use lambda greater than or equal to 0 for this under the principle that when we brought it into the Lagrangian, we relaxed the constraint. Therefore, the restricted problem, a maximization problem with the addition of a constraint will only have its objective function value reduced. So, lambda will be greater than or equal to 0. So, the conditions that we have are lambda greater than or equal to 0, first derivative del fx minus lambda del gx equal to 0 is exactly written as written there. Then lambda I gi of x equal to 0. Now this comes from 2 times lambda I si equal to 0. Now the s is nothing but, so this is g of x plus s square equal to 0. So 2 lambda I si equal to 0. Now s is, so this would give us either lambda I equal to 0 or si equal to 0. So when lambda I equal to 0, we can simply write lambda I gi of x equal to 0. When s is equal to 0, then we get g of x equal to 0. So we can write it as lambda I gi of x equal to 0. So this form actually captures 2 lambda I si equal to 0, except for the fact that we have eliminated the variable which is the slack variable that we actually added into this problem. Then g of x plus s square equal to 0 automatically become g of x less than or equal to 0. So the reason for writing it in this form is the original problem did not have the inequalities. The slack variable was added to convert the inequality into an equation, and then we use the method of multipliers. Therefore, at the end this is to be written in a form which does not have the s square. Now its use of lambda is inevitable because we have to convert this inequality into an equation. So we eliminate the variable s that we have introduced here and write it in this form, where we write it in terms of lambda and in terms of x. We leave out the s as such. Now this form is called the Kuhn-Tucker conditions. Also called Karush-Kuhn-Tucker conditions, depending on the contribution of the 3 people. Now this provides us with a general set of equations and inequalities to solve any nonlinear optimization problem with multiple variables, particularly when the constraints are inequalities. So this would give us a set of inequalities and equations. For example, you have a set of inequalities here. We have this is a explicit lambda greater than or equal to 0. You have a set of equations here, and these can be linear or non-linear or can have any power depending on f of x. Again, g of x less than or equal to 0 can have product form or quadratic variables, quadratic form of the variable depending on the g of x for a general non-linear programming problem. Nevertheless, once we write these conditions and write the resulting equations and inequalities, all we need is to solve this using suitable methods to get the correct value of x and lambda. Now with this background, we move to the central theme of this lecture series, which is the quadratic programming. Central theme in the sense that aspect of nonlinear programming that we are going to cover in this lecture series, which is quadratic programming. Now we use these Kuhn-Tucker conditions and then write down the corresponding Kuhn-Tucker equations for a quadratic programming problem, and then we show that the resultant system can actually be solved as a linear programming problem with some additional restrictions. So to that extent, we are going to do 2 things. One is we are going to derive the specific Kuhn-Tucker conditions for a quadratic programming problem, and then in part 2 we are kind of trying to show that this resultant system can be solved using linear programming, and therefore this will be shown as a linear programming application. Now the quadratic programming problem can be written as maximize or minimize z equal to Cx plus x transpose dx subject to Ax less than or equal to b and x greater than or equal to 0. Now we note a couple of things. Now x equal to x1 x2 to xn is a set of decision variables. Now the objective function is quadratic, that happens because of the form x transpose dx which gives us the quadratic form. There is also a linear portion in the objective function which is Cx. There can be a constant which can be ignored temporarily. So z equal to Cx plus x transpose dx represents the quadratic objective function. Remember that the constraints are linear, so it is written in the form Ax less than or equal to b, and all these constraints are linear. If the constraint is of the greater than or equal to type, it can automatically be written in this form. This can also handle equations and there is no difficulty about it. What is all the more important is x is explicitly stated to be greater than or equal to 0. In general nonlinear programming, whenever we have x greater than or equal to 0, it is treated as a constraint, but in quadratic programming we explicitly have all x greater than or equal to 0, which is actually pulled out of the resultant system. So this is the general form of a quadratic programming problem. This has several applications, and one of the common applications that one can think of is actually to look at a portfolio problem. If someone has an investment, a portfolio of say shares and other investments, then ordinarily there are two things associated with this. One is called the return and the other is called the risk. So here the decision variable will be how much proportion do I spend on each of these securities that form part of the portfolio. Now such that there is some expected return is greater than or equal to some r and minimize the risk, subject to of course the condition that sigma xi equal to 1, sum of the proportions of the investments should add up to 1. Now this problem is modeled as a quadratic programming problem because this risk is seen as a variance or covariance of the returns, and therefore it is a quadratic form. So the objective function is quadratic, subject to two constraints. One is a greater than or equal to constraint, the other is the sum of proportions equal to 1, and the third is an explicit condition that x greater than or equal to 0, because we do not want negative proportions of investment. So this is an application of quadratic programming to a real life situation. Now if we have a quadratic programming problem like this, and then we write the Kuhn-Tucker conditions here for a maximization. So the first thing that we will have is lambda greater than or equal to 0. So there are as many Lagrangian multipliers lambda here. In fact, before we do that, we also try and write it. The quadratic programming problem has an explicit condition that x is greater than or equal to 0, but the Kuhn-Tucker conditions are derived for a general nonlinear programming problem. So in order to write down the Kuhn-Tucker conditions, we actually write this also as a constraint and then write the Kuhn-Tucker conditions. So when we do that, we now get it of this form: maximize Cx plus x transpose dx, subject to the condition we have some g of x is equal to Ax or minus I minus B0 is less than or equal to 0. Now the Kuhn-Tucker conditions were derived for g of x less than or equal to 0. Therefore Ax minus b automatically qualifies because it is of the less than or equal to type. X greater than or equal to 0 is written as minus x less than or equal to 0. Therefore these two put together now forms the constraint set g of x. Therefore it is written as Ax minus b less than or equal to 0 minus, I am sorry, this should read as so Ax minus b less than or equal to 0 minus x less than or equal to 0. So this is the general set here. Now again we have n variables. m given constraints and again n variables here, therefore n constraints, because as x greater than or equal to 0 is treated now as an explicit constraint. So, now when we start writing the Kuhn-Tucker conditions for this, we would get, now we introduce lambda, Lagrangian multipliers lambda for this, and we also introduce Lagrangian multipliers mu for this. So, there are as many lambdas as the number of constraints, there are as many mu's as the number of variables. So, and we have as many x as the number of variables. So, we have n x1 to xn, mu 1 to mu n, lambda 1 to lambda m. So, this is what we introduce here, and then we write the Kuhn-Tucker conditions for this. So, this would mean both lambda mu greater than or equal to 0, because this represents all the Lagrangian multipliers. So, both lambda mu greater than or equal to 0, del fx minus lambda del gx would give partial derivative of this, which is c. So, this will become del fx will be c plus 2x transpose d, derivative of this del fx minus lambda del gx equal to 0. So, this will become minus lambda mu, because the set of Lagrangian multipliers, del gx will become, this will be ax on differentiation. So, you get a and minus I, so a and minus I equal to 0. So, del fx minus lambda del gx equal to 0 would give this equation for us. Then lambda I gi of x equal to 0 would give us ax less than or equal to, this would give us lambda I. So, this would give us lambda I gi of x equal to 0, and then we have g of x less than or equal to 0, which is given by ax less than or equal to b and x greater than or equal to 0, because g of x less than or equal to 0 is the same set of constraints that repeat here. So, that is given by ax less than or equal to b, x greater than or equal to 0. This one we are explicitly writing it exactly this way, and then we will make some modifications to this. So, we rewrite this and then make some modifications. So, lambda mu greater than or equal to 0, which comes from here. Now, this is written as, we keep this c on this side and take the rest of them on the other side, because this involves a variable x, these involve variables lambda and mu. Now, c is the only one that is a constant. So, we keep c on this side and take the rest of them on the other side, we would get minus 2x transpose d plus lambda transpose a minus mu transpose is equal to c. Now, this lambda a goes on this side, mu minus mu into minus I would give you a plus here, and when this goes to the other side you get a minus. So, this equation is written that way. Now, this one lambda I gi of x equal to 0 is now written like this. If we have for this set, now please remember that this is for a general Kuhn-Tucker form. So, this has to be written for both lambda and mu that we talk about. So, this will be written as lambda times, so if each one of these constraints will become ai xi minus b. So, this will be written as lambda I into ai xi minus b equal to 0, and this will be written as mu into x is equal to 0. So, this will be written as mu j x j equal to 0, and then we have ax less than or equal to b, and we have x greater than or equal to 0. I repeat again, now this one has been written from the Kuhn-Tucker form. So, this has to be written for both sets of constraints, this constraint as well as this constraint. So, when we have this lambda I actually represents both lambda and mu, lambda for this set and mu for this set. So, this will become some lambda I into a I x I minus b for the ith constraint here, and then this will become mu into x equal to 0. Now, what we do here is we now start introducing, this is the Kuhn-Tucker conditions that is written. Now, since we have Ax less than or equal to b, we can always introduce a slack variable s such that Ax equal to b or Ax plus s equal to b. So, this is written as Ax plus s equal to b. Therefore, this becomes lambda I si equal to 0. So, this becomes lambda I si equal to 0. Here we have a mu j x j equal to 0, and because Ax is less than or equal to b and x greater than or equal to 0, then we can always write this as Ax plus si equal to b or Ax plus s equal to b. So, now the Kuhn-Tucker conditions will become, now lambda mu greater than or equal to 0 comes from here, x greater than or equal to 0 is already here, and s greater than or equal to 0 has happened because we have introduced this s such that Ax plus s equal to b. So, we have now used this, we have now used this, we have now used this, we have now used this. So, now the Kuhn-Tucker conditions reduce to minus 2x transpose d plus lambda transpose a minus mu transpose equal to c, and we have Ax plus s equal to b. So, Kuhn-Tucker conditions reduce to these two things plus these two sets of things plus we have these. So, Kuhn-Tucker conditions now reduces to this plus this plus this. Now, if we look at all these carefully, now we realize that these are only variable definitions, So, we are okay with these being greater than or equal to 0. Now, lambda I si and mu j x j are not linear, they represent a product form here. So, these are some product form. Now, please remember how these two are got. Now, mu j x j equal to 0 is got automatically from the Kuhn-Tucker condition, which comes from this form. This was the original Kuhn-Tucker equation for every constraint. There are two sets of constraints, this and this. So, this was written for both lambda and mu, and therefore for lambda we got lambda I into a x I minus b equal to 0, for mu we got mu j x j equal to 0. Now, once, and we also have from here Ax less than or equal to b, x greater than or equal to 0. So, we simply introduced a slack variable s. Please note the difference that this slack variable s that I am talking about here was actually different from the s that was introduced to get the Kuhn-Tucker conditions, and we have first applied the Kuhn-Tucker conditions, and after applying the Kuhn-Tucker conditions, since we get Ax less than or equal to b and we know that x is greater than or equal to 0, we could always write this as Ax plus s equal to b and define a new slack variable s greater than or equal to 0. Therefore, in quadratic programming we will have slack variable s greater than or equal to 0. Now, after writing this, we realize that we can write it actually in 3 different pieces or 3 different sets. The first set are these equations which are got from this and this modified to Ax plus s equal to b. So, these two would give us, say, call this as 1 and call this as 2. So, this is 1 and 2. Then we get into lambda I si mu j x j equal to 0. So, I am going to call this as 3 and this as 4, and because s is defined as Ax plus s equal to b, so this will become, since this is Ax plus s equal to b, x equal to b minus Ax. So, this would give us minus lambda I si equal to 0, from which lambda I si equal to 0. So, this comes from 3 and 4, these two come from 3 and 4. then the rest of them are here lambda mu greater than or equal to 0, x greater than or equal to 0 and s greater than or equal to 0. So, the Kuhn-Tucker conditions reduce to solving these 3 sets, and we also said that this is like a product form. This interestingly is a set of linear equations. Linear equations because from the given one z is the only one that is quadratic, therefore the partial derivative of z with respect to x will give us a linear set of equations which are here. Ax less than or equal to b represents a set of linear inequalities, therefore Ax plus s equal to b would represent a set of linear equations. So, all we need to do now is to solve for 1, 2, 3, 4, 5, 6, all these 6 things put together, and each one, for example, this is a partial derivative with respect to x, therefore this will have as many equations as the number of variables in the problem. This is as many equations as the number of constraints in the problem. This product form is lambda I si both depend on the number of constraints, mu j xj both depend on the number of variables, and lambda mu xs are all variables. So, we have 2 times m plus n number of variables, where n is the actual number of decision variables, because both mu and x are from 1 to n, lambda and s are from 1 to m the number of constraints, and this will have the number of variables plus number of constraints. So, this will be m plus n. Here you have m product, n product, again m plus n sets. Here it is m plus n plus m plus n, so 2 times m plus n. So, finding out x lambda mu s such that it satisfies all this would give us the maximum or the minimum, assuming that the maximum or minimum exists and it's unique here, and we are not at the moment stressing on the second derivative to actually prove that it is a maximum or a minimum. We kind of restrict ourselves to solve this problem, understanding that whatever we get by the solution of this, by the unique solution of this, will be the corresponding maximum or minimum. So, now it boils down to solving these, and how do we solve this? Now, in order to solve this, now these can be written in a slightly different way. So, this can be written as minus 2d a minus I 0 a 0 0 I into x lambda mu s equal to b this will become c b and 0. Now, this comes because the first set can be written as, or this is not even b, so this is c b and 0. The first can be written as minus 2 dx, which is this form, plus lambda a, which is this form, multiplying by transpose, then you get minus mu, which is here, equal to c, which is here, and the other one is written as ax plus s equal to b. So, ax plus s equal to b. So, now this is the nice representation of this set of linear equations which are given here, plus of course we have this and we have this. If we momentarily leave out this, then and add, for example, x lambda mu s equal to 0, this is like solving a set of equations greater than or equal to 0. This is like solving a set of equations subject to the condition that variables x, lambda, mu and s are greater than or equal to 0, and these equations are linear equations. And we also have learnt much earlier in the lecture series that solving a set of equations subject to the condition that all variables greater than or equal to 0 can be modeled as a linear programming problem. So, this quadratic programming problem, whose optimality conditions reduce, or after applying the Kuhn-Tucker conditions reduces to a set of linear equations, a set of non-negative restrictions on the variables and a set of product relationship among these variables. If we temporarily leave out this set of equations or the product form, then we get a set of linear equations subject to this, which can be solved as a linear programming problem. So, in some way linear programming can be used, provided the linear programming iterations are suitably carried out to make sure that this is not violated. So, essentially we relax this, solve as a linear programming and make sure that at every iteration these constraints are satisfied, so that the solution of the linear programming with the additional restriction of these is obviously optimal to the system where we try to solve this plus this greater than or equal to 0. Now, all this we try and show through a numerical example, so that all these computations come out quite clearly. So, the numerical example that we would have is this: minimize x1 square plus 3 by 2 x2 square minus x1 minus x2 subject to the condition x1 plus x2 greater than or equal to 6 and x1 x2 greater than or equal to 0. Now, there are two variables, so x1 x2 that we have. There is a single constraint, so there is a lambda 1. Since there are two variables x1 and x2, there are two Lagrangian multipliers mu1 and mu2, and since there is only one constraint here, you get a S1. So, these will be the set of variables that we will have for x lambda mu s, x1 x2 lambda 1 mu1 mu2 S1. Now, again this is the linear portion, so this is your C. So, this first is written as maximize, because this table was set up for a maximization. So, we get maximize minus x1 square minus 3 by 2 x2 square plus x1 plus x2. So, that C or C transpose is 1 1. B, which is the right hand side, is 6. The constraint is x1 plus x2 greater than or equal to 6. This is a greater than or equal to constraint, but the Kuhn-Tucker conditions were derived under the condition that GI of x is less than or equal to 0. Therefore, this will become x1 plus x2 is less than or equal to minus 6. So, A will become minus 1 and minus 1. So, this will become x1 plus x2 less than or equal to minus 6. So, A will become minus 1 minus 1. Now, this from which we have to write to D. So, D will become 1 0, it is a maximization. So, minus 1 0 0 minus 3 by 2. So, that x transpose dx would give us minus x1 square 0 x1 x2 minus 3 by 2 x2 square. Now, we do not have an x1 x2 term here. So, if we had an x1 x2 term, say with a positive coefficient here, then this would come as something with a negative coefficient here. So, this divided by 2 should appear here, because the multiplication actually happens twice. So, right now we do not have an x1 x2 term, so we can leave this as it is. So, we do not have any difficulty about this particular thing. Now, we write this as, now we can use, now we have already, we know C, we know B, we know A, we know D. So, we can write it in this form and see how it looks like. So, right now the minus 2D will become 1 minus 2D will become this will become 2 0, this will become 2 0 0 3 is minus 2D. A is minus 1 minus 1 minus 1, I will become minus 1 0 0 minus 1. So, minus I is minus 1 0 0 minus 1, 0 is 0 0, and the third one will, the last one will be minus 1 minus 1, which is A 0, and then this 0 will be 0 0, I will be plus 1. So, this multiplied by x1 x2 lambda 1 mu 1 mu 2 s1 is equal to, we have C which is 1 1 and we have B which is a minus 6, because this is written in the form minus x1 minus x2 is less than or equal to minus 6. So now when we expand this, we would get 2x1 minus lambda 1 minus mu 1 is equal to, so mu 1 is equal to 1 and we have 3x2 minus lambda 1 minus mu 2 equal to 1, and then we have minus x1 minus x2 plus s1 equal to minus 6. So this is what we have here, and we need to solve this set of 3 equations subject to the condition that lambda mu xs greater than or equal to 0 and lambda I si equal to mu j xj equal to 0. Now when we write this, so here, and we also mentioned that this can be solved as a linear programming problem. So the first thing that we have to do, if we were to solve it as a linear programming problem, is to ensure that the right hand side values are non-negative. So this is multiplied again with a minus 1 to get x1 plus x2 minus s1 equal to 6. So it gets x1 plus x2 minus s1, which comes from this inequality. So x1 plus x2 minus s1 equal to 6. So we can leave out this particular equation, which is now rewritten as this. So we actually solve for 6 variables here, 3 equations here, subject to the condition that these 2 are satisfied and these are also satisfied. Now if we want to write it as a linear programming problem, then we have all equations here. So first thing we see or we verify is whether we can identify a basic variable. Now x1, and when we expand this in this form, we realize x1 does not have an identity matrix because x1 is here as well. It does not have an identity column because x1 is here and x1 is here. x2 does not have an identity column because it is present here and it is present here. Lambda 1 does not qualify because it has a minus 1 and a minus 1. Mu 1 seems okay, but mu 1 has a negative coefficient, therefore it does not qualify. Mu 2 also does not qualify, S1 also does not qualify. So in order to solve this as a linear programming problem, since we have equations, we introduce 3 artificial variables a1, a2 and a3, such that a1, a2, a3 now form the initial basis and the objective function automatically shifts to, so we add an a1 here, so this will become plus a1 equal to 1, plus a2 equal to 1, plus a3 equal to 6, and then we say minimize a1 plus a2 plus a3. So this is like the two phase method, where finally if we get a solution with z equal to 0, a1, a2, a3, which are currently the beginning basic variables, are out of the basis. So some 3 other variables get into the basis, and since all x lambda mu s is greater than or equal to 0, the moment we get a solution with z equal to 0, we have reached the optimum. So what we do now is we take these 3 equations, we add the artificial variables a1, a2, a3, and then we set up the corresponding simplex table, so that we solve this system, minimize a1 plus a2 plus a3 subject to this plus this plus this, with 3 artificial variables introduced into the problem. Now that we show here as part of this table. Now this is the expanded simplex table, where we have x1, x2, lambda 1, mu 1, mu 2 and s1, which are these 6 original variables, and as I mentioned, we need 3 more artificial variables a1, a2 and a3, which are also shown here as a1, a2 and a3. Now the first equation, which is written here as 2x1 minus lambda 1 minus mu 1 plus a1 equal to 1. So 2x1 minus lambda 1 minus mu 1 plus a1 equal to 1. Similarly, the second one is 3x2 minus lambda 1 minus mu 2 plus a2 equal to 1, and the third is x1 plus x2 minus s1 plus a3 equal to 6. So this is written here. these a1, a2, a3 being artificial variables have an objective function contribution equal to 1. So, the initial simplex table will look like this -3, -4, 0, 0, etc. And we should also remember that while we have to solve for this set, we also cannot ignore this and this. Now, this has been taken care of by the fact that we have formulated a linear programming problem. So, this not only minimizes a1 plus a2 plus a3, this is going to have x lambda mu s greater than or equal to 0, but then we have left this out. So, we have temporarily relaxed this. Now, when we solve do the simplex iterations, now this is for Cj minus Zj and this is for a minimization problem. So, the most negative Cj minus Zj will enter. So, variable x2 enters the basis. So, whenever a variable enters the basis, we now invoke this condition and make sure that this condition is not violated. Now, x2 enters the basis, the corresponding leaving variable is a2. Our condition is from here x2 into mu2 should be equal to 0. Right now mu2 is not in the basis, therefore, we can comfortably enter x2 into the basis. Only when mu2 is in the basis and x2 tries to enter, we can enter x2 only when mu2 leaves, otherwise we cannot do that. Now, we have to look at another entering variable such that these conditions are not violated. So, there is absolutely no difficulty in entering x2 here. So, x2 enters the basis, a2 leaves the basis. So, we do one simplex iteration to get a1, x2 and a3 as a new set of basic variables. Now, the original one, since the objective function values are 1, the objective function value is 8 here. Now, we can follow the simplex. Now, we have 4 and 1 by 3. So, 4 by 3. So, 8 minus 4 by 3 is 20 by 3, which has come here. And then at the end of this simplex iteration, we still realize that these two artificial variables are in the basis, and we also see that the most negative Cj minus Zj will enter. So, variable x1 enters. So, when variable x1 enters, we try to invoke this condition. The corresponding leaving variable is artificial variable a1. So, entry of variable x1 does not affect this because mu1 is currently non-basic at 0. So, x into mu is equal to 0 is satisfied. So, we enter x1, now a1 leaves, we perform one more simplex iteration to get x1, x2 and a3. We have still not reached the optimum because variable lambda 1 can enter the basis with a negative value. In some sense, we have not reached the optimum with respect to the quadratic programming because we still have not got a 0 objective function value. Now, lambda 1 tries to enter here with a negative value. So, again we go and invoke this condition, lambda I Si should be equal to 0. Now, S1 is not in the basis, therefore, lambda 1 can comfortably enter the basis. So, lambda 1 enters the basis and there is one leaving variable which is a3. Now, a3 leaves the basis, and now at the end of this iteration we have x1 equal to 18 by 5, x2 equal to 12 by 5 and lambda 1 equal to 31 by 5 with z equal to 0 and there is no entering variable. So, there is no candidate for entering variable, the simplex algorithm terminates, and in this simplex we have also ensured that these are not violated. Therefore, the solution that we have here with x1 equal to 18 by 5 and x2 equal to 12 by 5 is optimal with respect to the given quadratic programming problem, and the corresponding z can be calculated for x1 equal to 18 by 5 and x2 equal to 12 by 5. So, that is how the quadratic programming problem is solved. We can go back and now calculate the z for x1 square plus 3 by 2 x2 square minus x1 minus x2 and get the corresponding value of the objective function. So, this is how the quadratic programming problem is solved to optimality. Now, we wish to go back and show that this portion is like an LP application because the quadratic nature of the quadratic programming problem, when we apply the Kuhn-Tucker conditions, we end up getting a set of equations, a set of linear equations along with this plus this. Now, the set of linear equations with the non-negativity restriction of the variable is now solved as a linear programming and shown as a LP application to this problem. Now, the other important thing there is in all the simplex iterations we have to ensure that lambda I si equal to 0, mu j x j equal to 0. So, whenever a lambda or an x or a mu or an s enters the basis or tries to enter the basis based on the largest coefficient rule, we have to make sure that first find out the leaving variable and then make sure that the entry of this does not violate any of these. If it violates, then choose another variable which can enter such that there is a corresponding leaving variable and that these conditions are not violated. So, in a way it is not like just feeding a linear programming problem say into a solver and getting the answer, because at every iteration we have to make sure that these are not violated. Therefore, it boils down to looking at every iteration. It is almost like doing it by hand or putting another condition into the linear programming and solving it. Nevertheless, we can use the very fact that the objective function being quadratic, the only place where we have the nonlinearity coming is this form, and this is very convenient with respect to simplex because these variables are defined as basic and non-basic variables. So, a linear programming based approach to solving a quadratic programming problem is actually in place, and that is called the Wolf's method to solve quadratic programming problem. Now, with this we come to the end of the discussion of quadratic programming, and as we have already mentioned, we are only going to see one part of nonlinear programming, which is the quadratic programming. So, it is now time to recap what are all the things that we have seen in this lecture series of advanced operations research. So, we started off with advanced topics in linear programming. We looked at integer programming. We looked at network models. We looked at traveling salesman problem and vehicle routing problem, and then we also looked at a little bit of game theory, CPM and quadratic programming. So, these are all the things that we have seen in this course. So, here we saw several topics which largely which kind of helps us to solve slightly larger linear programming problems, and we use certain features of simplex or certain ideas such that we are able to expand the scope of solving linear programming to slightly larger problems and slightly specific problems and problems that have certain structures. So, we looked at even some varieties like goal programming here, where we try to look at multiple objectives and then come up with a meaningful way of trying to solve this. And one could also see that there was a lot of linear programming related stuff about complementary slackness conditions and so on. We also looked at column generation and solved cutting stock problems so that large problems can be solved. We solved using decomposition algorithm to solve a certain different types of linear programming problems. Now, integer programming provided us with a separate solution methodology, but again largely based on linear programming, but the idea either in the branch and bound or in the cutting plane, we solve problems that have an explicit integer restriction on the variables. Both the large focus was on cutting plane and branch and bound, and both of them in some sense used ideas from linear programming, and we also said that some ideas from here, some ideas from efficient matrix multiplication can also be used in solving here. Now, this in particular has tremendous real life application and potential. Then we move to network models, where the unimodularity nature of the constraints helped us develop LP based algorithms, even though they were integer programming problems, and each one of them used certain special feature of the network model to get faster and better algorithms than simply solving it by the simplex method. So, here we saw the shortest path problem, the maximum flow problem and the minimum cost flow problem, and certain various versions of this which were also solved using principles and ideas from linear programming, suitably modified for these types of problems. Then we moved to a set of problems, traveling salesman and vehicle routing, which were difficult problems, which were closer to integer programming. They were difficult problems. They all had integer programming formulations. Their exact solutions depended largely on branch and bound methods, which we studied in integer programming. And then we also had to look at heuristics, so that whenever we get into solving difficult problems, large sizes, it is absolutely necessary to provide good approximate solutions. Then we saw a bit of game theory, PERT CPM, and a little bit of quadratic programming. Now each one is an area in its own right, but then we introduced some of, as well as queuing theory. So we simply introduced some basics of each one of them. Queuing theory was the only topic that we looked at in this course, where we looked at some probabilistic kind of modeling. The rest of them could be seen as linear programming applications, even though each one has a lot of practical applications and each one is a separate field in its own right. So we complete this lecture series on advanced topics in operations research, providing the user with a set of tools which can be used extensively to solve real life practical problems. We hope this lecture series is useful in understanding the tools of operations research and learn more and more tools and techniques to solve real life problems. Thank you.